Welcome to This Explainer. Today, we're diving into how databases handle absolute chaos without losing a single byte of your critical data. If you've ever wondered how massive systems keep track of millions of moving pieces simultaneously without just completely falling apart, well, you're in the exact right place. Picture this high-stakes scenario for a second. What actually happens when you and someone else click buy on the very last concert ticket at the exact same millisecond? Managing concurrent transactions in a multi-user environment without crashing the whole system is, frankly, a massive undertaking. So today, we're unpacking the invisible architecture that prevents our digital world from double-booking reality.
Here's our roadmap for the day. We'll be hitting 1. The anatomy of a transaction. 2. Controlling the database state. 3. The chaos of concurrency. 4. Protocols and deadlock prevention. And 5. Database recovery systems. Let's jump right in.
Section 1. Anatomy of a transaction. Time to meet the real hero navigating our multi-user environment.
So at the absolute heart of all this is the transaction. You can think of it as a single, indivisible logical unit of work. Basically, it's an operation or a set of operations that accesses and possibly modifies the contents of a database. It's the core process we have to manage, literally the absolute baseline of how databases process our requests. Now, to actually pull this off, transactions have to follow the ACID properties: atomicity, consistency, isolation, and durability. And look, these aren't just fun acronyms to memorize. They are the unbreakable laws of database physics that guarantee data integrity. Every single transaction must strictly adhere to these properties to ensure the database remains totally consistent, regardless of what goes wrong during execution. A transaction actually lives a pretty perilous life. It wakes up in an active state, just processing data. As it runs, it might move to a partially committed state. If all goes perfectly, boom, it reaches the committed state, which means success. But if something goes wrong, it hits a failed state and ultimately gets aborted. Interpreting this flow is really your first step to truly managing database transactions effectively.
Moving on to Section 2, Controlling the Database State. Now that we know how a transaction flows, let's see how we actively manage these states in practice.
We take the wheel by applying Transaction Control Commands, or TCL. You can think of commit as the ultimate save game button. It permanently saves the changes made by that transaction. On the flip side, rollback is your crucial undo button. But, it's way more than just a simple undo. If a transaction hits that failed state we just talked about, rollback ensures all changes are wiped, reverting the database to its previous clean state. That way, half-finished, corrupting data isn't just left lingering around in the system.
But what if you're executing a massive, multi-step transaction? You definitely don't want to lose the whole shebang just because the very last step failed. That's where save points come in. Rather than rolling back an entire massive transaction, a save point creates a partial safety net, an intermediate marker. It allows the system to roll back just a specific part of a transaction, which adds incredible precision to our control commands.
Section 3, The Chaos of Concurrency. All right, let's introduce the villain of our story, simultaneous execution.
When 1,000 users make demands at the exact same millisecond, the sheer volume of activity is just staggering. Our core objective here isn't just speed, it's absolute, uncorrupted consistency. We have to keep data perfectly accurate, even under immense pressure, ensuring strict isolation so that all these simultaneous processes don't just crash into or corrupt each other.
So, to maintain this order, we rely on serializability, specifically conflict and view serializability. Think of conflict serializability as making sure individual read and write operations don't step on each other's toes. View serializability, on the other hand, is a slightly looser rule. It just ensures that the final output looks exactly the same, even if the internal steps got a bit jumbled along the way. Both rules guarantee that all this concurrent chaos still results in a correct, logical sequence. It basically makes it look as if transactions happened perfectly one after the other.
Section 4, Protocols and Deadlock Prevention. Let's figure out how to prevent crashes in this insanely busy data intersection. To keep the data highway moving, databases use strict traffic control protocols. We can contrast lock-based protocols, which basically act like stop signs, forcing one transaction to wait at the intersection for another to pass, against timestamp-based protocols. Those act more like a strict ticketing and scheduling system based on exact arrival times. Both of these aim to solve conflicts and maintain totally smooth system execution.
But what happens when these protocols accidentally create a trap?
Imagine transaction A is waiting for a lock held by transaction B, but transaction B is waiting for a lock held by transaction A. Nobody can move forward. This is the dreaded deadlock. It's basically a mathematical standoff that will instantly freeze your entire system if you aren't prepared for it.
So how do we beat the standoff? Mainly two ways: detection and prevention. With deadlock detection, the system actively scans the background for these infinite standoffs and forcibly breaks them apart. With deadlock prevention, the system establishes really rigid rules up front to ensure a deadlock scenario can mathematically never form in the first place.
Finally, Section 5, Database Recovery Systems. Time to explore what happens when the protocols fail, the power cuts out, and we absolutely need an ultimate safety net. Because let's face it, even with perfect concurrency control, systemic failures happen, and that's when we apply powerful recovery concepts to save the day. Log-based recovery keeps a meticulous, chronological journal of every single action. If the system crashes, it's like rereading a diary to carefully reconstruct the database step by step and literally fix the past. Shadow paging, on the other hand, creates a hidden, duplicate map of the data. If things go wrong, it's like instantly swapping a broken engine for a perfect spare. Both of these are there to rescue your data when you need it most.
To wrap up this explainer, I really want you to think about the systems you rely on, or maybe the ones you're building yourself in Module 5. If 1,000 users hit your databases right now, where would your infinite standoffs happen? And exactly which protocols would you deploy to stop them in their tracks? Keep analyzing, keep building, and I'll catch you next time.